Welcome back to video lecture series on design of compression member. In steel structures, the outcomes are students will able to identify and classify the compression member. They will understand the terms like effective length, slenderness ratio, understand behavior of compression members and factors affecting its strength and performance, and calculate the least radius of gyration. Two families. First one is member subjected to flexure load and other is member subjected to axial load. In the previous unit, that is beam and plate girder, we dealt with members subjected to flexure load. Now coming back to axially loaded member, there are two types of axially loaded member, tension as well as tension or compression. So this is a compression member which is subjected to compressive forces along its axis. The vertical members in a building are generally called as post, column or stanchion. A compression member in roof truss is called strut. Compression member in a crane is called boom. We understand that behavior of column actually depends upon its unsupported length. Column which are short are subjected to crushing and behaves like a member under pure compression. Column which are long tend to buckle out of the plane of load axis. As we have already seen that performance of column is a function of its length. Actually it is effective length. So effective length is designated by KL, where K is the length factor which depends upon the end restraint condition. End restraint condition is nothing but the support or end condition of the column. So there are two types of end restraint which we will discuss. One is rotational, other is translation. These are the definitions of effective length which is given in class 7.2 and this definition is given in 1.3.35. So continuing our discussion on the translation and rotational restraint, start with relative translation or position restraint. This means that end of the column is not free to change its position, but rotation about the end can take place. As you can see, this point and this point, the end points of column are restrained. They are not allowed to change its position and they are free to rotate. What about rotational boundary or directional restraint? In this, the column can change its position, but rotation about the end of the column cannot take place. That means the end of the column is free to change its position, but rotation is not allowed. Now the third case, which is shown in this figure, figure B, it shows that when an end of a column is having restrained in position and direction both, then the end is not free to change its position and the rotation about the end of the column also cannot take place. This is a case of fixed end. Neither there will be any translation about this direction or this direction, nor there will be rotation at the support. Whereas this is a hinge case. This one is hinge and this one is also hinge, where translation is not possible either in this direction or in this direction, but rotation is allowed. Moving ahead, you can see this is a pin-pin combination. That means translation is not allowed, but rotation is allowed. So the combination of restraints about either or both the axes, they can be classified as both ends of the columns are hinged. This is considered as standard case, hinge, where effective length is equal to unsupported length, where capital L is the actual length of column. Now the second case is both ends of the column are fixed. It can be seen in figure B. Both the ends are fixed. So how will be the deflected shape? There will be restrained in rotation as well as displacement or translation at the support. However, beyond a certain distance after the support, the deflected shape will be like this. So this is a combination of hinge and fixed support. One end is fixed, that means translation and rotation is not allowed here, whereas in case of hinge only translation is restricted, whereas rotation is allowed. So case 4 is the case of fixed and the other end is free. So this is summary of the effective length of prismatic compression member. Prismatic means the cross section of the member is same throughout the member, right? So this is given in table 11 in page number 45. So the first one is, this is fixed. We'll go with this value. The value of K for fixed end will be 0.65. As we already discussed that hinge case is the standard case. So in hinge case, the value of KL is equal to L only, because value of K is, theoretical value of K is 1 and recommended value is also 1. So this is the standard case, right? So in case of combination, that is one end is hinge, other end is fixed, we'll take K value as 0.8. So whenever we calculate the effective length of compression member, we will use table number 11. So now we started with the consideration that behavior of column is a function of its length, but now what we can suggest is behavior of column is a function of its effective length. Now we can change our statement. But in actual practice, actually the behavior of column is a function of slenderness ratio. So to understand what is slenderness ratio, it is a ratio of effective length by radius of gyration. What is radius of gyration? It is a geometric property of a section, which is nothing but mathematically it is under root I by A, where I is the moment of inertia of the about any axis and A is the area of the section, right? So how we will get the radius of gyration? The radius of gyration of all the rolled steel section can be obtained from steel table. It is available in steel table. And once we have calculated the radius of gyration, we can easily calculate the slenderness ratio. Now this is an example, numerical, where we will try to find out the radius of gyration. So this is a built up section. We can see that it comprises of a I section, IS HB 450. It is a heavy beam, IS HB 450, and it is having two cover plates on either side of the flanges, right? Both the flanges are having cover plates. Now in this we want to find the radius of gyration, and very specifically it is written as we want to calculate the least radius of gyration, right? So we will calculate IXX, IYY, then we will calculate the area of the section, then we will calculate the radius of gyration, and we will see which is about which axis least radiation of gyration takes place in case of I section or a built up section. So what will be the value of moment of inertia of the compound section? It will be equal to moment of inertia about y axis of the plate, then moment of inertia about y axis of the H section and similarly we can calculate the area of the compound section. It is equal to area of I section, which you will get from steel table, and area of the two plates. The size of plate is 700 by 18. So when we calculate this, we'll get the total area in centimeter square. So now we'll calculate IY. IY, we can see that plates are actually rectangular. So what is the value of moment of inertia of a rectangular plate? It is BD cube by 12. So B is the width, dimension parallel to axis. So what is the axis in this case? Axis is y axis. This is the y axis, right? So what will be the dimension parallel to y axis? It is 18. So B will be 18 and depth will be 700. Depth will be 700. So what we will write, BD cube by 12. So what is B? It is 1.8 centimeter into what is depth, 70 centimeter into 10 to the power 4. It makes it 2 millimeter to the power 4 into 2, because there are 2 plates. So twice of BD cube by 12 will get the moment of inertia about y-axis of the plates, and moment of inertia of the section about y-axis you can directly take from steel table. So the compound section, IYY of the compound section will be IYY of plates plus IYY of section. So total will get as 105,945 into 10 to the power 4 millimeter to the power 4. Mind you, the units, moment of inertia unit is millimeter to the power 4. Now we'll calculate the least radius of gyration. It is IY by A. So once we have calculated slenderness ratio, and we have already concluded that the performance or the strength of column actually depends upon the slenderness ratio, and we know that for efficient design, slenderness ratio for a compression member should be as small as possible, so that material can be stressed to the greatest possible limit. See, as a designer we want to optimize our section. So for optimization and to bring economy, reduce the cost and weight of the structure, what we do, we'll use a slender structure, right? And it should be capable of taking all the loads, and it should be serviceable also. So code has specified in table 3, page number 20 of IS 800, that the maximum value of KL by R, that is slenderness ratio, is limited to 180. It is limited to 180. You can go through this table as and when required. As per numerical we can see it, right? So the limiting value of slenderness ratio as per IS 800 is 180. Now what are the factors that affect the strength? So it is very obvious that material of the column, obviously if you use a stronger material, the performance will be better. In the present case, or in the present subject, material is constant, that is we are using steel. So this we can say that it is actually the modulus of elasticity, E of the material. Then the second parameter is cross-sectional configuration. It is basically I, moment of inertia. Is it rectangular, it is square, it is I section, it is hollow? So cross-sectional configuration, it essentially means that moment of inertia. We have already seen the effective length of column, then the supports. Effective length actually depends upon the length of the column and restraint condition, the end condition. And these are the residual stresses and imperfection that will be there in the column section. To take care of all these imperfections in the column, code has given provision for value of alpha. Alpha is imperfection factor, and it has classified all the section into 4 classes: class A, B, C and D. And value of alpha for class A is 0.21, for B it is 0.34, for C is 0.49, and for class D, buckling class D, it is 0.76. So this is an important part, that what alpha is used, basically it is imperfection factor. There can be eccentricity of load which we are not knowing. There can be material is not isotropic. We are assuming that material is homogeneous and isotropic. There can be some geometric variations in the column which we as a designer we are not aware. So to take care of all the uncertainties of imperfection in this section, code has given scope for value of alpha. Now how we will classify this section? Generally for I section, generally for column or post or stanchion, these are the vertical members in a building, right? So these are vertical members in a building. We use I section. Either it will be rolled or it will be welded. Suppose we are using rolled section, then what we have to do, we have to check whether the thickness of flange is less than 40 or it is greater than 40 and less than 100, right? Then we have to compare the value of h by b. What is h? H is the overall height. You can see from the figure, This figure is also given in page 44 of the code. You can open that and then check what is h. H is the overall height of the rolled section. What is b? It is width of flange. So you divide this h by b, the ratio. If it is greater than 1.2, then buckling class about z-axis will be a and buckling class about y-axis will be b. Suppose the ratio h by b is less than 1.2 or equal to 1.2, then buckling class about z-axis will be b and buckling class about y-axis will be c. In case of welded section, we see that if it is very simple now, if the thickness of flange is less than 40, buckling class about z-axis will be b and buckling class about y-axis will be c. And if TF is greater than 40, then buckling class about z will be c and buckling class about y will be d. So you can check this figure and get certain with it. Built up section, for built up section, the buckling class is always c. For built up section, the buckling class is always c. Then modes of failure. There can be various modes of failure. We have already discussed that. Long columns will have buckling and torsional failure, whereas short column will have crushing failure only. So as a designer, we are more concerned about buckling failure because the buckling load is quite less as compared to crushing load, right? So these are some of the figures that are showing the local buckling and squashing of the member. You can read it, it is self-explanatory. Now what we see is these are the design steps. When we do the numerical, it will be easy. We'll see in next class. Okay, so this is the formula which we will use for design of compression member. It is load is equal to permissible stress into effective area. Stress into effective area. So effective area generally will get it from steel table, or you can calculate it through calculators also, right? With the given data we can easily calculate AE. So the real challenge will be to calculate FCD. So for FCD we have to use this table. This is table number 9 and there are 4 parts of that table, curve A, curve B, curve C and curve D. So depending upon the section classification we will use the chart, and whatever value we will get, we will check it for Fy is equal to 250 only. So 2 parameters we will consider to calculate design compressive stress. First one is lambda, that is KL by R. The other one is classification of section. So we will get the values of FCD. Sometimes we have to do interpolation also. So we'll put this value and we'll get the value of PD. So if we are not going to use that curve, we have this formula Fy by gamma m0, where gamma m0 is known to us 1.1, Fy is 250. There are 2 terms, phi and lambda square. So what is phi? Phi is equal to 0.5 alpha into lambda minus 0.2. What is lambda? Lambda is nothing but under root Fy by FCR. What is FCR? FCR is equal to pi square E upon lambda square, right? Pi square E upon KL upon R whole square. So when we put FCR in this, we will get lambda. When we put lambda and alpha value from that table, we will get phi. Then we can put all this value, we will get FCD. Now another term is zeta. Zeta is another stress reduction factor is there, which we can calculate, right? So in the present semester we are not going to use this method. We are simply concentrating on calculating the FCD from the chart number or table number 9. So these are the various options of using various compression member, angle, single angle, double angle, T. These channels, they are essentially used in trusses, right? These are used in trusses. Wide column or heavy column. They are used in for post or columns. And this circular section, they increase the hollow section, basically increase the torsional capacity of the section. So this plate built shape of columns you have also seen in railway stations and many steel structures you have seen this. So these are also commonly used as compression members. So these are the sum of explanation of how you select cross section for span, and depending upon the requirement what configuration we will use. You can read this, right? So these are the example. This is a wide column section, right? Depth and width are more or less the same. So these are generally used as a column. And this is a normal I section, or a normal I section is used as a post or a column. So that's it. You can go through this presentation I have already shared with you, and in next class we will start the numericals, right? Okay.